Hopefully, you can see my presentation slides now. Before I start, I just want to say that if anyone is having a hard time hearing what I'm saying, that that's because I'm struggling with a bit of a cold at the moment, and there isn't much I can do about that, unfortunately. So if there's anything that's unclear, please feel free to ask me to repeat myself. So the title for this presentation is I'm going to talk about a technology-independent description and configuration of algorithms for evaluation of student responses to mathematical tasks. An alternative title would be criteria graphs for automating feedback generation, but I will talk in more detail about what all this means very soon. So I work at Imperial College. I'm a postdoc involved with the Lambda Feedback project together with Peter Johnson and Phil Ramsden and a few others there. Okay, so the outline of this talk is that I will discuss a tool that lets a task author, and I'll talk about what a task is, or what a task is in this context in a moment, to easily assess and modify sort of the broad behavior of a system that automates feedback generation so that will actually generate the kind of feedback that they want, if possible. So I'm going to talk a little bit about background and motivation, the design goals. I'm going to describe this concept of criteria graph, and I'm going to have a brief note on how we have looked at some collected responses from students to try to decide how to work with this in a good way. So for the purpose of this presentation, whenever I say a task, I mean something that a teacher gives a learner that is designed to be challenging, but it's intended to support in learning rather than be part of an assessment. So independent study rather than exams. And this task will involve that the learner is expected to produce some kind of response. And we have some way of deciding that the task is completed, or well, in the sense that maybe it's time to move on and try another task if this response has some set of properties that then depend on the specifics of the task. So just I'm going to give a couple examples. So a common type of task that is appears in mathematics or subjects that use mathematics is that you have some reference expression known by the task author, and the learner is expected to, through some chain of reasoning, figure out what reference expression they're asking for. In this case, we have an example from fluid dynamics that we're asking for an expression for the drag on a submarine given a linear wake profile. In this case, the reference expression is this pi rho over 6, and then u squared and r squared are physical quantities. So, well, we can think of those as variables. So in this case, for completeness, it's enough to check one, well, criteria, determine one property of our response. And that's the, I should probably say reference expression here. Answer here is the same as the reference expression concept. So if the response or the candidate expression is the same as the reference, then we're finished. But there can, of course, be cases where we have other criteria that are also interesting to know. So, for example, if the response divided by the answer, then if that is a constant, that means that they have the right physical quantities involved, but there is some factor missing. Well, a constant that isn't one, I should say. And there are also things like sign changes might be meaningful, and more specific physics things, like it might be that you have the right quantities involved, but in the wrong way, so you get the wrong dimensions of the expressions and things like that. So this structure can appear in many circumstances. Another example that is fairly popular when you're trying to introduce a new concept to help a student understand, you ask or you suggest that the student create their own example that matches this. And here is an example from cryptography. So we ask the learner to produce 3 integers n, e, and d that together form a suitable RSA cipher key. There are infinitely many correct responses to this, so that would be typical, a large set at least of possible examples. But we can write them down as a fairly small set of criteria to check. In this case, there are 3 different criteria. And then there are also other interesting criteria that if we, for example, look at if this E is co-prime to the Euler totient of N, that can give us some information. Well, if it isn't true, then it will give us some information of what kind of mistakes might have been made. There are also sort of aspects where you can argue that it's not a suitable RSA cipher key if it's easy to break. It's easy to for someone else to decode your encrypted message. And there are various strategies for checking this that can also be formulated as criteria about the response. You can also have even more freeform kind of tasks, so derivations or other kinds of simple proofs where you want to, for example, show the equivalence of 2 expressions using some set of valid rewrite rules. So then the response would be a sequence of statements, and then you check in each step that this is a valid way to rewrite it and that it starts and ends at the 2 expressions that you want. And there's also various kinds of, for example, drawing a diagram that has the right features. If you're drawing a circuit, you want it to have the right topological. If you're drawing the graph of a function, you want them to pass through a certain number of, or a certain set of points, or have the peaks in roughly the right place, or be fairly smooth, and so on and so forth. For the purpose of this talk, this simple kind of expression comparison is the task we will be having as a reference example, just to limit the scope of what we're talking about. So then we sort of need to ask ourselves, what is a well-designed task then, and what is good quality feedback? So for the purposes of this discussion, I'm not going to take any kind of philosophical stance on how education should be done. I'm going to assume that whoever is doing the teaching knows how to do it well enough, and that the key to success is to give them the tools that means they can do what they want. So that is the main goal here. So really, we want to empower the task author as much as we can. Of course, if we're working with an automated system, there will be limits to what it can do, but then we also want the task author to quickly realize what those limits are, if they need to use another system, or if they can create workarounds themselves. Yeah, I'm gonna skip those points. Also, we're focusing on just looking at single tasks, not the larger scale sort of process. How do we help students understand how to deal with maybe a certain class of tasks effectively, and strategies for that? This is, for the moment, focused on only the single task. So some aspects that we in the Lambda feedback project are trying to keep in mind or work towards is that we want timeliness of the generated feedback. So we want it to come at the speed of thought of the students. Essentially, we don't want the student to have to wait for a teacher, for example, to grade their work. We want them to get it automatically, and the teacher should be able to trust that the system produces reasonable results. And we wanted to do this fairly quickly. So ideally, well, less than a minute, ideally much less than a minute in most cases. Next, we want repeatability. So that means if you have 2 student responses that are the same or substantially same, this can of course mean very different things. If we are comparing 2 expressions where we care about if they're mathematically equivalent, or if they are written in the same way. If we, for example, ask someone to factorize a polynomial, the polynomial on standard form and a factorized form are equivalent, but they haven't completed the task. And also we want this to be reliable over time. So they should get the same response the same feedback for the same response at different times. That you can create questions where the correct answer changes over time as well, but that should be a deliberate choice. And then ideally, we would also like the feedback, at least without effort, again, from the task author to change things. If you have two similar tasks, they should give similar feedback so that we can compare things both across tasks as well as within cohorts that solve the same task. And next we want quality, and this is quality in, well, two different aspects, or one. Things are interconnected here in a non-trivial way. So it's important that the feedback that the students get is high quality. But in order for that to happen, we also need to have a task authoring experience that is high quality. So we need to be able to use whatever technology that is most appropriate for a certain type of task. It needs to be, when we can, consistent and predictable and learnable so that it's worth the effort for the task author to learn how the system works. It needs to be, again, configurable and flexible so that the task author can do what they want. And we also want to collect useful data so that we can look at the responses and make improvements to our educational material in some way. And of course, there is no point if the system has all these nice properties if no one is actually using it. So final point is what we call viability. We both want a low barrier of entry, so that it's easy to learn, easy to use, to get started. We want it to be compatible with other types of academic materials and softwares. It's important that we can contribute in many different ways to it. So we want it to be extensible, we want it to be improvable. And also, if a teacher invests a lot of time and effort into making something that's worked with our system and then loses access to it for some reason, for instance, by moving institutions, we want them to be able to replace, or at least feel like they can replace the system with a reasonable amount of work. So we want it to be sort of the important choices that they made when designing their tasks. Those should be able to be taken out of the system and realized using some other way. And what we're hoping to achieve by that is, if we do everything manually, then we can produce high quality. That's the assumption, but we lack in timeliness and repeatability, and it's hard to reuse others' work, or limitations at least. But with good technical tools, so for example, I that work full-time on this, I can create code that I can reuse. I can create large amounts of tests that I can reuse. And we can set this up so I can create questions where, well, someone else can create a useful task without needing to understand that code. But we still need another step in the sort of quality of tools for communicating to the task authors how to use the system well in order to actually reach high quality. Okay, so this is intended to be used with the Lambda feedback platform, which is a currently deployed platform used by Imperial College or parts of Imperial College. We can use any technology we want for evaluation and feedback generation. It's timely, so it's, like I said, mentioned before, less than a minute response on most things. And currently we have a wide audience with varying requirements for rigor and complexity of mathematics. We have about 30 active teachers, 1,000 active students, and 100,000 or so pieces of feedback generated per month. So, well, if you do the math on that, you realize that if we do that manually, it would not be a lot of time per piece of feedback per teacher. And we want the authors here to be able to think like teachers, not like programmers. So authoring tasks should be more like writing a solution or a grading guide than programming or writing code. And we don't, since we can use different underlying technologies, we can't assume familiarity with a particular one, but we also, again, want fine-grained control over these feedback generation and evaluation functions so that we can get the behavior we want. And we also want to collect information about what mistakes or other properties we can see in the responses so that we can do data-driven improvements of our educational material. So the design goals for our tools here is that the task author should be able to focus on defining what is needed for a response to be considered correct, complete. So a small set of criteria that is enough. And then from that, ideally, the feedback generation system should then already suggest or handle a lot of the cases of common mistakes for you already. We also want it to be, again, easy to learn. So we want the task authors, if you ask the system to behave in a certain way, you should be able to see the consequences of that in or at least an overview of the consequences easily. And then we want, again, empower the authors to adjust if there is some part of behavior that's not satisfying. And then we want this description to, again, be platform independent because we want to use it many different technologies, and we also would like to be able to use it completely outside of the system. Okay, so I'm going to just introduce a small tool here that I've called a criteria graph, which has, well, it has a few different kinds of nodes. I will show you an image soon with examples. And the feedback generated by this graph is what we get if we traverse it in a certain way, depending on the properties of the nodes and the particular response. So here is an example of a very simple criteria graph. All we do is we want to compare two numbers and we check that they're real numbers. So the criteria that are interesting to the task author are down here on the left. So what we're probably expecting is that the answer should be equal to the response, but of course mistakes will happen in one of the other two criteria instead. And then above these criteria nodes, well, so if we have established that one of these criteria nodes is true, then we have completed it in a sense. So I'm going to call this an output node. But in order to determine what is true, we need to do some sort of evaluation. So we have this compare answer and response evaluation node. But if you want to compare two real numbers, you need to check that they're real numbers. And that's the kind of thing we don't want the author to have to worry about. They should only pick which of these criteria are interesting. So once we've done that, we can use this, what we call a sufficiency map, to determine what other parts of this graph do we actually need to look at to make sure everything works. So say we start with answer equals response. That's the criteria the task author wants. We go back and check the preceding evaluations and see that, well, we need to, before we can do this, we need to establish that the answer is a real number. And in order to do that, we need to start at this top evaluation node here. For simplicity here, if you have, at least if you have a very complicated graph, especially if it involves loops or similar, you can turn this into a tree format to make it a simple flowchart. So again, we start up here with, is the answer a real number? And then we can just go down the tree and see what will happen in different cases. So what I'm going to do is that I am going to show you a little demonstration of this. So hopefully you can see this. I know that unfortunately the font size is quite small here. And here we can see, so this is the same tree or same graph in tree form that I have shown, but with slightly different formatting. So again, our blue nodes with rounded corners, those are our evaluations. Our reddish nodes with square corners, those are our criteria. And then our green oddly shaped nodes here, those are our outputs. So we start again. Here we just compare if 2.1 is the same as 2.1, which is true, and we can establish that 2.1 is a real number, 2.1 is also a real number, and that they are equal. Maybe I should just ask here if there is anyone that would like to suggest another pair of numbers they think it would be interesting to compare. Pi, that's a good suggestion. So let's see if pi and 2.1 are the same. In this case, they're not. In this case, it does say that the answer is smaller than the response, which I believe is a mislabeling. I'm very sorry about that. Should have fixed that. Complex numbers would be interesting. There is a little bit of a notation issue in this particular demo, but what we can do is, well, let's keep pi because that's a real number, but we can make the response some form of expression. So say it's x squared plus pi, and then we try that. Is this not updating for some reason? Oh, sorry. Okay, sorry about that. Small technical issue. Let's get back to it. Oh, let's just have a simple example where we can see that if I turn the response into an expression instead of a real number, it can detect this and go to the wrong, or and say that this is an error, this is an invalid response. Yeah, so let's see, 2 and 4, will that work? Yep, it recognized that 2 to the power of 2 equals 4. Yeah, I think that there are a fair number of people here that come up with suggestions that once you're at this point, it's actually fairly easy to play with this system to understand what the evaluation function is doing. But I am going to go back to my presentation. There we go. A final point that I'm not going to put much emphasis on is that the way criteria graphs work, they can be built, a large and complex criteria graph can be built from simpler criteria graphs. And you can do this in a way that means you can essentially treat them as a substitution grammar. So it's a common design in these kind of automated systems that you get a lot of functionality by combining smaller parts, a library of standard functions or something like that. And once you can do that, you can then simply create criteria graphs for each component and then combine those criteria graphs into larger, more complex things. But what you show the task author is only what is the system doing right now. You don't need to show the full complicated implementation with all the details. So in this case, I've split this graph we had before into, we have our compare answer and response part, and then we would have 2 of these is X a real number graphs that we would substitute this part with in a certain way. Okay. So I think I have spent most of my time now. So I just want to conclude with, hopefully, I've described well why I believe that powerful author tools is very important for ensuring quality of automated feedback. Hopefully, these are very small and simple examples. I would be glad to provide a longer or another presentation with more describing more complex behavior of this in the future if there is interest. And you could see that we can both examine the behavior, and you can also see which part of the graph you would need to change the behavior. So you can enable that kind of adjustment. And our plan is to deploy something like this to teachers sometime during this year. So we can look at, I just realized I forgot something that I promised to do. I am very sorry. Let me go back to my earlier example. I think I have the... So I mentioned this example with the linear wake. So when this is an actual question that exists on the platform at the moment. And briefly after deploying it to students, we realized that, or the teacher realized, I should say, that this mistake where the students drop a factor was very common. But there were quite a few different variations of what factors they were missing. In fact, I think for over 2 cohorts now, we have collected about 700 responses, and there's about 170 unique ones. So trying to predict them all or even trying to grade them all by hand would be a lot of work. But only by adding, so essentially three criteria. I'm just gonna pop up my table. So if we then check for if the expression is not equal or if we're missing a factor and that it's not a product, that covers almost all of the mistakes that the students have done in this case. And we can see what the rough distribution of the different mistakes were. Yeah, unfortunately I don't have my table has gone missing, so I can't show you the details of the numbers here. You're gonna have to trust me that they exist. So this does mean that adding a few criteria or working with the graph, we can then adjust the behavior and get a better understanding of what is going on. And we plan to deploy this to teachers and see it actually used in practice and see if a larger number of individuals agree with me that it seems to work fairly well. And then I always want to say thank you very much for listening. And I believe we have time for questions, and I will gladly answer any questions we don't have time now if you contact me by email.
Great, that's brilliant, Karl. Thank you very much. That was a lovely presentation. If people either put their hands up or write questions into the chat, then we've got a little bit of time for questions there. So one that's come in from Karen, I'll read that one out for you. It said, students can see the error message. Can clues to the correct answer be included in those?
You give me a moment, I'm going to show you what the students see here.
Great, thanks.
So this would be what the students see on Lambda feedback. I hope you can see this. Then I need to look up what the actual correct answer is because I have not taken this class. So if I put in, first it shows you a preview here of how is what you've written interpreted by the system. So the students can see that, well, this is what I intended. And then if we check it, in this case, it only tells us it's correct. But let's say I remove the divided by 6 factor. In this case, it then tells us that there is a missing factor because the teacher has put in this extra case.
Okay, and I'm assuming that you can add to that, can't you?
Yeah, so you can add to that. I mean,
well.
there is a separate, there is one problem is determining the properties of the response and then determining what you know about the response into useful text for the student.
Yeah.
And I haven't discussed the second problem there, but if you have the data, at least you have somewhere to start.
Okay, and there's another question in the chat, which is, how do you envisage this being used with existing assessment systems?
So when it comes to existing, one thing, like I mentioned before, it's a common design that you have a sort of a library of standard functions that you can combine in different ways to create them, tasks. And if you then can hook those up to automatically create criteria graphs, that would be one way of using it. We are also working with others to try to see how we can set it up so that our platform can call other people's assessment systems rather than just what we have made ourselves. Because again, that's sort of the viability, that we can cooperate and that you can. A lot of these projects, they work very well for a few years and then they lose funding or someone retires and then it sort of stagnates or stops working and then you need to replace it with something else. So this is also that you have that persistent description of the behavior you want. And then you can try to see how can I adapt this to a new system if you need to switch.
Okay, thanks, Karl. Any other questions from people? While people are just thinking about other questions there, Karl, I was just going to ask myself, what sort of pushback have you had from people trying to, as you've tried to engage them with this?
My experience been that it's hard to explain the concept, but once you show them a demonstration, it's usually much more positive. So that's why we're working hard on trying to get this in the hands of people so we can see some interesting things being made.
Yeah, so it's really just sharing it around. And there's a question from Tom, which is sort of linked to that previous question, which do you think this could be used to write marking algorithms for numbers? So I don't know if you've crossed that
I'm
system.
superficially familiar with numbers. So there needs to be maybe a clarification here. So the criteria graph is intended to describe the behavior of an existing algorithm. So when you create the algorithm, you would also create a describing criteria graph. The criteria graph is not meant to specify the behavior. So this could be something that would help a teacher understand how a particular marking algorithm works. Or could be, for example, if you notice in your trees that one of the evaluation nodes behaves differently than expected, you could communicate with, say, the numbers developers on, I would like this behavior to change. There's a bug here or there's something strange. Or at least you can try to find a way to, by adding criterias and connecting them to your tree in the right way, create your own workarounds without needing to get involved with development yourself. So it should be easy for developers to create the trees. It should be easy for task forces to understand the trees without understanding the underlying code.
Okay. And there's a comment really in there as well, which others far more knowledgeable in the room about this sort of thing than me might want to pick up on as well. That says that Stack uses similar evaluation feedback trees with maxima trees in the nodes. I know Chris was in earlier. I think Tim Lowe and George Kinnear are also in here.
I am somewhat aware of that as well. I haven't actually used Stack to the point where I can tell exactly what the overlapping functionality is. But I mean, any tree can be written as if while statements. So in a sense, you could argue that the logic structure it describes is used in many different systems. So this is more a matter of how to demonstrate it and adjust it.
And do you think that's the main value of this particular system, the sort of being able to see that?
Yes, it's
okay.
It's intended as an interface between the task author and the code.
Okay, I've just lost my chat window momentarily because there was one more question in there. Okay, so question from George, which is, do the response and feedback need to be exactly the same? That they're talking there in terms of, length, if you put a character on the end of it, or, spaces in there or whatever it might happen to be. Is it a real proper matching?
So this would depend on the system. What we use in Lambda feedback now is fairly flexible in terms of using different notation and implicit multiplication and having white space before and after or in the middle or all of that. So we tried to set it up so that students can think as little as possible about the sort of syntax of typing into the box. I'll try to keep it close to the kind of flexibility you can have with handwriting. We even have handwriting so that they can write in a little box and it tries to interpret it for them. So that largely depends on the particular evaluation function used. But yeah.
Okay, thank you very much. Are there any final questions before we wrap this session up? In which case, Karl, it leaves me to say thank you very much for a really interesting session. I'm sure people have gone away with lots of things to think about there, and it'd be really helpful as well as you sort of socialize this a bit more with people in terms of what kind of feedback you get from that as well.
Yes.
So thank you very much for coming to give this session, particularly as I know you're not feeling 100%. So thank you for working your way through that. And I don't know, Michael, is there anything you want to say about next sessions again?
No, I think it's just a reminder that we have a next sort of double header seminar session on Wednesday, the 21st of February, and then we move into kind of a more extended workshop program. So do sort of keep checking your emails for the latest Tower information. If you want to contribute to any of these events in the future, please do let us know. And just thanks again to Karl for great session today, and particularly doing so well a bit under the weather. So thanks, Karl.
Oh, thank you very much. And thanks to everyone for listening. And again,
there's just one quick question that says, do you know the times for the next seminar on the 21st? I think it's 2 o'clock, isn't it?
It will be 2 p.m. Yeah.
It will be 2 p.m.